Now we'll just see some sample problems in tuned amplifiers. So design a tuned amplifier. See, we don't have FET, we have only BJT. Okay, so you whatever in FET you can neglect. We'll go for the transistor-based tuned amplifier. A tank circuit has a capacitor of 100 picofarad, inductor of 100 microhenry. So you know a tank circuit is LC parallel. L and C values are given. The resistance of inductor is 5 ohm. As I told you before, an ideal resistance, the ideal inductor will have zero resistance. The practical inductor will have a very small amount of resistance, which is because of the wire. So here the value is 5 ohms. Determine the resonant frequency, impedance at resonance, Q factor, and bandwidth. So resonant frequency is very simple. You know, F naught is equal to 1 by 2 pi root of LC. Substitute for L and C. You are getting the resonant frequency as 1.592 megahertz. At resonance, the impedance is given by Z naught equal to L by CR. You know, at at resonance, it becomes a pure resistance. At resonance, your circuit becomes a pure resistor. So the resistance value is given by L by CR, or 200 kilo ohms. You know Q is equal to omega naught L by R. So you know general formula for Q is X by R. X can be either omega naught L or X can be 1 by omega naught C. So you can, however you do, you will get the same answer. The Q value is 200. Bandwidth equal to F naught by Q. We found out F naught. We found out Q. Bandwidth is 7.96 kilohertz. So one important observation, what you should do for tuned amplifier is the bandwidth will be very, very narrow. Usually bandwidth will be hundreds of kilohertz, but see here it is only around 8 kilohertz. It is very, very small, which means that it is a highly selective network which will work only at one particular frequency, this 1.592 megahertz. At this frequency, you have maximum gain. Other than this frequency, wherever you operate, it is going to provide gain which is lesser than the peak value. Okay, so that is what we have in the unit 5.